delivered. So. Well, welcome everybody. You know, although it's not written there, we still welcome you, and despite of the weather, it was great to see you all. Well, the name of the talk is Metrology and Laser-Based Material Processing. This has something to do with what the company does. So we are the company that pretty much does the processing with the laser beam of any materials. We cut and with the goal of cut as small features in the materials as we can. So we went to micro scale. Right now we're going to sub-micron scale. Our goal is go small, or whatever wavelengths will allow us to do. And to do that, we need to optimize certain parameters of the business. Certain parameters of the lasers. So we're dealing with two different things. The lasers and the materials. And in the lasers, there are not so many parameters to optimize, like wavelengths, pulse energy, pulse rep rate, pulse widths, beam quality. And wavelengths determines the color of the laser and determines the absorption, of the material that you have. So any material lacks certain wavelengths. Like for example, if you just shine the light through the piece of glass, the green light, it just goes through. It's not being absorbed. So presumably, if you measure the energy before and after, that piece of glass does nothing to the light, unless you try to delay it and so forth. We want the material to absorb the light, so we want that laser beam to do something, so energy has to be transferred there. And in this case, wavelengths is very important. The pulse, the energy in the pulse, of course, you can have a huge energy in the pulse, but the material cannot take it all. Everybody in this world is trying to resist anything that comes extra to him. So if it's too much, it will be pretty much rejected by the material. And like for example, if you're shooting the piece of metal with the laser beam, all of a sudden the plasma, the electrons are being extracted. They go up, and it's so-called screening effect. And that electron cloud screens your sample from the rest of the pulse that's coming in. So as much as you want to throw in, you can. And there are pulse repetition rate, pulse widths, but the most important parameter is also beam quality. And this is where the new upcoming lasers and improvement in the laser technology, improving the lasers, so bringing the beam quality to the theoretically diffraction limited beams is taking place. And also then we're dealing with materials. And materials have different properties. Materials have different conductivity, different type of hardness and so forth, So we are dealing, unfortunately, with all of it. We can't disregard one simple property of the material that we have there. And to talk about the metrology here, how to measure it, will just take many papers, many talks. So what we decided to do in this talk is just talk only about the tools and only about the processes that we develop here at Lenox Laser. And to my own surprise, it was quite a few. And here there's some effects of the laser beam on the material. It can cause microcracking, it can cause melting, it causes carbonization. Carbonization is when you look at the material, it's like it shows up like a black area, black spot on the surface of the material. So in other words, your material makes the chemical composition with the carbon there that it's very hard to remove, almost impossible. And in case of metals, you have to do like etching and so forth, chemical etching. So, and if you have a composite material such as alloys and so forth, you can drill the hole. Let's just consider it just a very simple thing. We're drilling the holes, but you can destroy the stainless steel. Why? Because I mean you supply so much energy to the stainless steel. All of those composites that go in alloy, they go to their own centers. They don't like to be mixed together because the process of making stainless steel is a very sophisticated process, you know, multi-step annealing and so forth, certain temperatures. All of a sudden you're destroying that. So yes, you can drill the hole, but at the same time you can destroy the material. And in this case, all those previous parameters of the lasers that we mentioned before become very important. And then if you're just drilling the very long channel, you know, choosing the wrong parameters makes those micro particles inside of the channel, inside of this channel. And because of that, this is the example of one of the systems that we built here and we're using. You see those three conduits here. Sorry for showing it with, you know, my finger there, but it's actually three different wavelengths that we're using there. So one single laser, we can't leave just with one laser there. And you can see the setup here. You know, we'll give you a tour. So, is General? We'll give you a tour, so we'll explain you more. And it's like the QC is always built. You see the picture of our QC manager there. So it's in every process the QC is built in. You know, we can just, you know, go without that. We have all the feedbacks in the systems. We have cameras, but the human factor is the most important thing. I'll just give you the short glossary here because down the talk, one of the directions that the company takes is to serve pharmaceutical industry. And in pharmaceutical industry, one of the most important things is to package the, package their products. While packaging the products cannot be vulnerable to the bacteria, viruses, so forth. And but what happens is a very simple thing: is once the product is being shipped, just imagine you have a vial with a hole in it. All of a sudden, defect, right? And the contents of that vial is being taken on the airplane. So all of a sudden, the pressure on the airplane is less than the pressure inside of that vial. So the material from the vial is being pushed out of that hole, presumably. Okay, that's fine. But what happens when it lands back? You know, the pressure on the ground becomes smaller than the pressure in that vial, you know, anymore. And then everything is trying to move back, you know, inside of the vial. And in this case, you can have a very serious contamination. So what our company does, we're generating the standards. We're generating the standards for the industry to test their instruments, you know, that they're being used for so-called integrity study. And in this case, we're calibrating that particular leak. Those standards have the calibrated leaks. But how do we do it? There are a few terms here, and I'll explain to you just in the next slide, like flow effective diameter. The crack can be any type of a shape, and nevertheless, you have to some sort of come up to a certain metrology to calibrate that. The aspect ratio, all the channels, I'll explain you like next slides too. All the channels have different length, different diameter, and those parameters are very important. Also, it's an absolutely different impedance of every channel to that bacteria or to anything else, you know, because if you're talking about biological issues, you know, some of those bacteria just grab on the wall, some of them just like this smooth wall, some of them, and so forth. That's why, you know, when they're making the materials, there are new studies that's showing that everybody was trying to use the stainless steel tops, you know, in labs. But they figured out that the stainless steel tops, I mean, are the easiest thing for the bacteria to grab on. They're so smooth, it's easier to grab one. While if you have the corrugated surface, it's harder for them to grab one, you know, and stay there. It's like counterintuitive stuff. We're using different type of meters here to measure those leaks, you know, when it comes to, you know, the flow products. We can measure the volume there, and I'll show you tons of the instruments that are down there. Volume versus time, and it becomes, we call this type of measurement is volumetric measurement. We can measure the mass of the material. It's either the gases or liquids that are going through that hole versus time, and it's mass flow measurement. Laser parameters I already explained, and we're using a few instruments here: SEM, scanning electron microscope, and we're using the automatic microscopes later. Flow effective diameter. Just imagine you have tons of different cracks in the material, and you have to simulate that crack. We have to make that leak. How would we do that? It's very easy. You just drill the round hole where the area of this round hole is equal to all of those. I mean, any area of the crack. And pretty much the diameter of this particular hole is being called the flow effective diameter. Right? And in terms of the aspect ratio that we mentioned before, just imagine this is the sheet of the material, and this is the length of the channel, this is the diameter of the channel, and although it's drawn here not to the proportion, this diameter may be micron, and the thickness of the material can be a few thousand microns. So we successfully, I don't see Arlen in here, but he's flying in from with Jonathan DeMayer, you know, chief of our production. We, few years, sort of pioneered that method in drilling the channels here with aspect ratio of a few thousands in glass. You know, it's very hard to select the metrology methods of measurement depending on the products that we use, because the company serves few markets. One of the markets is the optical market, when we drill in very thin films, metallic film and so forth, and we are floating photons through that. In other words, it's being used in the optical industry. They shine the light through that, the laser beam, and they can use it as a spatial filter there, where they can choose the good portion of the beam. They can use those different shapes of the holes to generate different type of diffraction patterns for their own use and so forth. And in this case, the geometrical parameters, the geometrical shape, the circularity, and the quality of the edge are very important. So we can use the standard the same standard to calibrate that, geometrical patterns and so forth. For the mass flow volumetric method, we use the standards that are just calibrated flow orifices there. SEM, as we know, using a very tiny spheres that actually NASA is bringing a lot of those. The Smith is the representative of NASA, so I know who is in the room right now. So he used to be the chief of the metrology for the whole agency. So, and one of the businesses that NASA does, on a shuttle, then there's no gravity there, and small nanoparticles are being generated, then they're being brought in, and they're being used, those nanospheres, to calibrate the microscopes there. A lot of guys are using the bubble detection. What happens is sometimes it becomes almost impossible to find the leak there. Like, just imagine you have a container there, and you have to look for the hole in the container with the regular shape, with, you name it, flexible container. So what people do, they just take this container, put it in the water, One of the methods you can use the gas tracing. I'm just concentrating on maybe 1% of what's being used in the industry, but we did it here, so only something that's relevant to Lenox laser. So, and you can submerge that in a water, put the pressurized gas in that, and then start looking for the bubbles, and then start counting the bubbles. And by knowing the diameter of that bubble and pressure, blah, 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 you can pretty much determine what's going on. And believe it or not, it's being very actively used in the industry, I found out, because the video tools became very usable nowadays. So they pretty much can monitor the whole bubble stream coming from all type of the holes distributed on the surface. If you have an array for samples, they not only they're looking for the leaks, they're sometimes looking for the calibration. And depending on that, what you measure, you have to choose the tools. You can choose all of those tools, and it really depends on what you're measuring. You know, what do you want to measure? The godfather is the regular microscope, although just it's surrounded, you know, it's one of the microscopes that we have on the floor, you know, and where you can just look, and at a certain magnification, you just can see and make a picture of the geometrical shape on the of the feature that is being drilled. And by changing the focus, you can also go so far in depth and generate the profile of that. The second version of that is just more modern. You know, it came from optical gauging procedure instruments. This is automatic microscope. You have an XY platform and Z platform going up and down, and you can look at your samples, and pretty much this is what you see on the screen. You can look, and it has statistics built in. It will generate you the circularity, all type of you know, other measurements that you're looking for. And this is one of the examples of the tungsten aperture. And that black hollow thing that you see over there in circles, you know, this is from very old measurement. This is that carbonization that I was talking about. Sometimes in the industry we call it the heat affected zones there. This is the picture of the SEM, and once we give you a tour, Dr. Otis is sitting in white shirt, modest over there at the very end of the room. He is a grandfather of those instruments. We have a few of those, and they have their own use when we need to resolve on a submicron level scale, you know, certain features. Or look, that's another picture of the same microscope. Look at the structure of the materials, and this is the example of those. Just look how the holes, I mean, although if you do the flow measurement or you do optical measurement without this magnification, they will look perfect to you. They'll be all circular. But if you zoom, like you see there on the picture to the very in the right top corner, you know, it's very interesting figure. And believe it or not, I mean, if you drill 1,000 holes in this particular material, they'll look exactly the same like a fingerprint. You know, the big question is why. So we're trying to collaborate with like two scientists to find out what is causing that and actually use that. And 20 nanosecond, 5 picosecond. This is the pulse width of the laser beams. So that material was done in Alloy, I think that's a Kovar or Inconel, something of those, the top picture with the picosecond laser. So the physics is absolutely different. See, you see some melting around here, that's a clean hole. You know, you see some other defects, like material was ripped off at the very end of the material, or we're just trying to analyze that and improve the process later. And actually, this that was Kovar. And you can see this is the same picture, analogous to the one that I showed you before. And tons of those holes right here, they look exactly alike. You know, they're very, very small holes here. And the scale here is 1 micron. So this micron, so it's pretty much maybe 10 micron hole, 5 micron hole here. This one is, I have to put my glasses in, so it's very small, but I believe it's 875 micron holes. And then we use some other type of processes. On the bottom corner, you see the hole that is not just made by laser, but we use some post-processing on that. You know, and you see it's like very round, has nothing, no melt or anything like that. So we have some proprietary processes that even involve the mechanical processing of that, not just electrochemical or laser to do that. So, because there is not one single tool in the world that will give you all. You have to have all the lasers, all type of processes that you have. That's an example of the porous materials. And sometimes, you know, those packaging, you know, if we stick to the pharmaceutical products, the packaging needs to involve the porous materials because it has to breathe, you know, but at the same time, the hole has to be large enough for the air to come through, but it has to be small enough to block any type of the contamination by bacteria or anything else. They use that, and they still need to calibrate that. So the question becomes, I mean, okay, we can drill in this material, but how do we calibrate it? Because there's it's spec'd with an open area. In other words, it has like, let's say, half of a micron or micron holes already built in by the methods in this material there. And if we drill one, how do we measure? So we limit the area, you know, we limit the area there. We blow the gas through the area with no hole in it. We find out, you know, what's the leakage of that particular area. Then we drill the hole there, and using the same area compare by the deviation. Okay, the leak shall increase by so much and so much. And it's very interesting. The pictures are done actually on electron scanning microscope because it's impossible to resolve all those pictures further. And you can see we tilted the sample a little bit so to see the depth, you know. And so this is another example. Let's see, this is what laser beam does. If you try a few more, they'll look exactly like this. So that's examples of what's happening on different type of materials here that came from different manufacturers. And this is two sides of the material. This one side of this material is multi-layered. That's another thing. You know, that how would you calibrate, what the metrology you can come up with to calibrate something in multi-layered material. You need to use something to look at, and, you know, like we did right here, geometrically define the diameter, but what is the diameter in this case? It's very hard to understand. We don't even know what the shape of the channel inside of that. So in this case, we're using the cross correlation with all other methods. We will trying to use the optical microscope, we're trying to use electron SEM, we're trying to use the flow measurement devices, and it helps us actually to cross-calibrate those because, depending on the length of the channel, it's not the hole, the diameter of this hole is not the only limiting parameter. It's the impedance of the whole channel that by measuring that becomes important in this case. And we are behooved to go in that area and just do that with different instruments. And because of the complexity of all of above, FDA came up with this scale where if manufacturers are calling, they can pretty much relate to a certain class, 1, 2, 3, 4, 5, 6. They did it for simplicity. And what it does, it correlates the leakage rate to the orifice leak size. Like for example, if they're saying that the hole is between 0. If defect or whatever hole is between 0.1 and like class number 2, 1 micron, you can expect the leakage rate of microcentimeters squared per second there, from micro to hundreds of microns rate. And in this case, it was very interesting to find it because the data is based, all those standards came from the data that was supplied by Lenox laser years and years ago. We were invited to FBA and give that talk. So if right now the metrology goes a little bit further down to make the thing simple. So instead of just people asking you what rate do they want or whatever it is, they can refer to a certain class, you know, and you already know and they already know what they're looking to detect and so forth. There are a few different parts, a few different major ways how to control and calibrate the orifice. One way is to do the in-line testing or in-process test. Another one to do the post-measurement. Sometimes you have to do you have to do 2 of those and sort of combine those 2. And in process we sometimes call it drill to flow or dynamic measurement. What it means is we are measuring something while we're drilling it, pretty much. When we're creating some sort of a structure, a slit or whatever it is, we can measure it right there, and then we can do the post, measure it afterwards. But to do the built-in process is the hardest thing because the picture of our QC there is not, sometimes it's not enough to do it. We have to do some mechanical, some embedded testing there. And those processes are usually deterministics. They're not, we're going away from stochastic processes, although sometimes we don't have enough statistics or don't have enough samples to calibrate our system in such a way that will give us the good precision of the instrument there. So in this case, the post-measurement takes place. So in other words, after the sample is being done, we measure it, and do the analysis. And those methods sometimes are impossible to do without destroying the sample. So we do the sampling, we design it by the request or by the reliability and repeatability of our instruments. And we know that we have to pull each 5th sample or 10th sample out of that, destroy it, measure it, just to determine the long term of stability of our instrument there. And these are, I just simplified a few flow equations here on the board that will just show us what are we doing. This is the diameters here, flow affected diameters. This sign is pretty much being proportional to. So what we see here is if we measure the gas, the gas, the diameter is proportional to 1 of the square root of the inlet pressure. In other words, if our inlet pressure just goes up like 4 times, our diameter will be reduced only twice and so forth. And it's fourth point, it's very slow dependence on molecular weight and temperature. So in other words, for the gases, the system, the idea of this slide is just to show the sensitivity of the instrument. So the system is very sensitive to the change of the pressure and not that sensitive to the change of the temperature and molecular weight. And if we flow the liquid, liquid is almost non-sensitive to the temperature at all. And a specific gravity is a ratio of the weight of the liquid to the weight of the water. So, and while you're doing that, you really have to understand the requirements for your environment in this case, right? Because sometimes keeping the temperature of your instrument, the temperature of environment is very important. Sometimes it's not. Keeping the pressure becomes more important, and so forth, so forth. Those equations are very simplified. You don't see the dependence on the channel lengths and so forth there, but they're there. So it just gives us the idea to understand what's going on. And here you can see the picture of one of our homemade volumetric flow measurement devices. Here, I don't know if you've seen the water columns. You see the plastics. Okay, it's another slide that gives. In industry, this method is called bucket and a timer method. So in other words, you have a bucket of water with known volume. You just open that up and you click your timer to find out how much time does it take for you to empty that particular bucket. So in volume versus times becomes the flow, right? So you measure the flow of this time by doing the volume. And you can see there are tons of valves depending on the orifice diameter. You know, guys are choosing a different type of a volume. What happens in this instrument is very, very simple. So I like this instrument. It's literally transparent. It has water in it, water is transparent, and the physics of this method is transparent also. What happens right here, I don't know if I have one more. Yeah, there's device. You put the gasket or something with known hole or unknown hole right here. You squeeze it. It's just this portion comes in, and then you start blowing gas, you know, and gas displaces through that, and gas displaces the water. And then we have like photo interrupters and so forth. We use the constant volume, and we measure the time. And of course, like volume versus time becomes a flow. Then a little bit later with Frank, he's an engineer, Frank Rabach sitting over there, we decided that we were so smart to go ahead and scale that huge instrument into something smaller like that. The main reason for that, we wanted to measure it came from a need to measure the smaller holes, you know, very, very tiny holes. So instead of those huge columns with water that you saw on the first slide, this thing has a capillary tube. What was the diameter of that, Frank? It's like half a millimeter or something like that?
The total volume was 1/10 of a cubic centimeter. I can't recall leak.
Yeah. No, the leak was 0.1 SCCM, I think, 0.1 micron, right. So, very tiny. And we thought, okay, you know, you can see like a few photo interrupters that slide back and forth and so forth. We thought the instrument should work, no, but it didn't, you know. And we struggled, and we found out that we are against the capillary effects inside of this instrument. Then we're trying to measure the hole or the leak that comparable with 0.1 micron hole there. So just imagine what type of, so we need to be at least by Nyquist like twice as better. We need like to be 0.05 of a micron to measure, I mean, so 50 hundredths of a micron just to measure it. So, and it was not trivial to do. We found out the leaks, the temperature, everything affected that. But what happened, once you start from that, it leads you to tons of other instruments because you're trying to modify it. And this dynamic flow measurement instrument came from that particular instrument there. Because that instrument, the first one, it did not completely not work, but it was unstable, and it required a lot of calibration prior to starting. And if you're in manufacturing business, you can't afford the setup times being like hours and hours before you even start the measurement. You need to go press the button and go there. And the sample here goes right there, and I'll explain you the method of this instrument is very simple. What we have there is, that's an interesting thing. You have the bottle, right? And you need to drill the hole in that particular bottle and measure. So while it's under the laser beam. So pretty much what you do is you put the gas in, and this is just two conduits. It's just a splitter, and the gas fills out everything over there. So, and then you look at the manometer and you look for the steady state. So in other words, I'm not blocking anything, am I? Okay, I'll move to the other side. So you look at the manometer and you watch that needle not to move. So that's step number one. That means that everything is pressurized exactly the same. Then what you do, you close one of those branches over there, and there is your calibrated orifice. And you start drilling there, start creating the leak there, and the mass flow sensor will see any change. So in other words, if there is no hole there, there is no flow in the gas, there's no pressure differential. Once you start creating leak in there, the gas will start flowing through the mass flow sensor, and it will measure that particular flow. So that instrument came from the first one. And this is one of our other volumetric flow measurement instruments. I will show you those. We have tons of those pretty much next to every station. It's sitting on the floor. There's like a vacuum pump and all other components. The idea is we measure the deviation in pressure. So, if there is a leak, we calibrate it with a known orifice. It goes to the steady state, nothing changes. Then we open the leak up and we look for the steady state again. And I know there are NIST representatives here, so we're being influenced by NIST. We have a calibration stages here. So in other words, this stage measures nothing, it just helps us to calibrate our own stages that are being used for our own process there. That very last one, I think it's one of the last slides, or very last slide, is there is another method that we tried here, and I think we'll go back to that. It's called diffraction measurement there. A lot of products, as I mentioned before, that Lenox laser does are associated with the optical products. In other words, we take this thin foil, metallic foil, and we cut very round hole and a very slit in that, and we need to measure that really well. And it's a big volume of those products that we're making. And the end user is using those particular products to generate that diffraction pattern. In other words, if you just take the hole and you shine the coherent light through that, coherent light means that this particular has supposed to have a few properties. The wavelengths does not deviate, and all phases move together. In other words, if you just shine the laser beam through that thing, and you'll see some sort of interference pattern if you project that whole thing on a screen. And depending on the quality of the edges and roundness and so forth, you will have and sharpness of the edges. You'll have a certain contrast of those rings over there. So this is what the industry is looking for there. So we years ago. We are not using it anymore, but you know, if need comes, we can resurrect the instrument and so forth. We pretty much created exactly the same thing, you know, as a detector as they're using for their own purposes. And what happens there? We can measure the diameter. If you know the wavelengths of the laser, in other words, if you know the color of the laser that you there, and that wavelength nowadays is even on your flashlights, it's plus minus 2 nanometers. That's very, very stable sources, you know, with those laser diodes nowadays, you know. So in other words, if the wavelength is about 600 nanometers, having plus minus 2 nanometers is very good precision for the wavelength. So this one we know real well. And diffraction order is just the number of those rings that you see on the screen. And you need to know the distance from here to the screen really well, measure that one. And that's everything that you need to do. Well, I'm sorry, all that you have to know to determine the diameter. So, but with new cameras coming on the market, you know, where you can put this mega and megapixel cameras, you can design that all instrument being in one package. Just put the aperture in, calibrate the whole system, and it will show that to you. You know, but unfortunately, the end user, or you know, the catalog houses, whatever, they dictate you know, how do they measure. So if they really want to measure it's geometrically and having plus minus 1 micron, whatever it is, a certain deviation, we have to follow up. We have to follow up their process and do it exactly the same way. But this is with again with new cameras. We might resurrect. We may go back to that and resurrect that thing. And it's once again, the metrology of that is only good for the thin films. In other words, if you don't have a very thin sheet of metal, and a very thin sheet of metal means less than 10 micron sheet of metal that we have there, the contrast degrades, because the thicker the material, the well, contrast in this case is the ratio of the bright spot to the black spot, the number of the photons there. So it will degrade a little bit because every surface of that channel will be re-emitting the light, you know, and that would be hard to do. So I know we started too late, you know. I wanted to make it short. If you have any questions, I'll be happy to do this.
I have a question, Greg.
Yes.
In your, when you're using the gas flow for your measurement processes, what media are you using for gas? Is it an inert gas, or is it air, or what is it?
Oh, we're using, it depends. We're using sometimes these very selective gases, you know, dependent on what we're calibrating, which instrument. But for those water displacement comps, we're using the mostly air, the dry air, you know. But we, you know, if we need to go into the more precise things, we're substituting that air with a known gas. Yeah. The problem is a little bit different. All those equations are oversimplified. The dependence is not really square dependence, it's high order dependence. And we generated the empirical data, and then we generated the fit function, put that back in there, and we have it on the, it's not the easy transition, but that's a very good question because it's the most sensitive to that, right? Thanks. So I did not do good, right?
No, you did great.
All right.